So this last topic in chapter 3 then is related rates. These are kind of good word problems. Before I get to the word problems, let me show you. What we've learned in the last couple days, we've learned about implicit differentiation. So I'm kind of building up to this topic when I ask you this. Watch this now. If I say, take this derivative with respect to x, it's now an implicit derivative. It's not a difficult one. Implicit differentiation was in section 3.5, and we talked about it a couple times. I don't know how hard you've worked on it yet, but it's good. But it's not that hard. If I want to take this derivative with respect to x implicitly, then here I go. I've taught you to just walk into him. If you're doing it with respect to x, then this is kind of a normal derivative. You call it 2x. But when you do a y variable with respect to x, how do you do that? 2y. And then you tack on this little dy dx. You know what? If you wanted to, oh, by the way, let's finish this. You get across to the other side of the equal sign, and the derivative of 1 is 0. So then there's your derivative, dy dx, and we like to solve for it. As I was doing this, one way you could think is that, after you do the derivative of an x variable, you could think that you tack on a little derivative of x with respect to x. Now, I never talked like that before, and it's really redundant, because what is that? 1. Thank you, it's a 1. So, but maybe it helps you understand that maybe every variable you run into, you take the derivative of that variable with respect to x. I'm taking the derivative with respect to x. But when I do an x variable with respect to x, it's very redundant to write this, because it's just a 1. So you've never seen me write that before. But when I do a derivative of a y variable with respect to x, I multiply by this dy dx. But that is a 1. I don't know if that thought helps you, but I'm leading you someplace here, you guys. Just to finish this, you know what to do. To solve for dy dx, you move the 2x over, you divide by 2y. And if you don't mind, very quickly in my head, move the 2x over, divide by 2y. I'm getting this as an answer. Move the 2x over, it's negative 2x, divide by 2y. The 2's cancel. But that's a classic implicit derivative. I really am not trying to teach you this implicit differentiation. I'm reminding you of it because here's what I want to do. I want to walk into what we do in section 3.7 is we walk into these equations and we're talking about rates of change. Then we get into word problems, good word problems. And I'm starting with not really a word problem. But we write an equation about the word problem, and then here's what we do. Listen to this. We take the derivative implicitly with respect to time, with respect to t. That's what we're going to be doing in 3.7. Now look at this equation. Do you see any t's? I mean, there is no t's. That's okay. We have x probably is a variable that depends on time, and maybe y is a variable that depends on time. And here's what I want to do. I want to take this derivative across the board with respect to time, t. So do you think you know how to do it? I sort of just taught you something maybe. I mean, here's what I want to do. I want to walk into this and take the derivative with respect to t. Okay, so when I run into an x, how do I do the derivative? I do a 2x. But then I think I should do the derivative of that variable x with respect to t. How do I say that or do that? I write dx dt. And that's the rate of change of x with respect to time. But I needed that. I walk into the y term and I take his derivative with respect to t. That's 2y dy dt. I walk into the number 1 and I take the derivative with respect to t, which is 0. So this is a brand new idea. In related rates, I want to tell you what I'm doing. I am taking the derivative. I take the derivative or do the derivative with respect to t. And what's funny is there's no t anywhere in the equation. I mean, we have x's and y's, we have volume and height, we have area and radius, we have all kinds of situations, and we take the derivative with respect to t. A classic question, I'll get to your question in a minute. A classic question is a word problem like this. Watch this. This is a classic question. An oil tanker is spilling oil into the ocean. And it's spilling oil and it's laying across the ocean and it's forming a circle. And the radius of that circle is growing at a rate of, I gotta make something up, 60 feet per minute. Now, hang on, what am I saying? I'm saying an oil tanker is spilling oil. It's forming a circle out there in the Gulf of Mexico. Maybe we're up here in a helicopter looking down on it. Is that okay with you? All right, we're looking down on it. It's a circle, but this circle has a radius that is growing. So it's growing. And I just told you that it's growing at a rate of 60 feet per minute, right? So what did I just tell you? I told you the rate of change of the radius, right? Is that what I just told you? The radius is growing at 60 feet per minute. When you read that, and you didn't get to read it because I didn't write it down, I told it to you. When the radius is changing at a rate of 60 feet per minute, when you read that, what I've just told you is not the radius, but the rate of change of the radius. You know what I just told you? dr dt is 60 feet per minute. You know, analyzing the units might help you. The numerator is a change in r, which I guess is the feet. The denominator is a change in t, which I guess is some minutes. The rate of change of the radius with respect to time is dr dt. I just said this circle is growing. The question is, watch this, the question is how fast is the area changing? How fast is the area changing? Now listen, am I asking you for the area? No, I'm asking you for the rate of change of the area. You got to be able to read that. And so, and what is the rate of change of the area? How do you write that? dA dt. That's what I'm asking for in this sentence. How fast is the area changing? And maybe I could have said with respect to time. Maybe that would have helped. But what is the rate of change of the area is what I'm asking for. So the radius is growing. Of course, if the radius is growing, the area is growing. And what we have is, that's why this section is titled Related Rates. What's going on in this problem is there's a rate of change of the radius, and that's related to the rate of change of the area. I mean, it does make sense. If this radius is growing, the area is growing. But we always ask you these questions at a particular instant. So when I ask how fast is the area changing, I have to say at the instant when I'm making this problem up, when r is 200 feet. When r is 200 feet. Okay, this is a classic question. I gave you the rate of change of the radius. I'm asking for the rate of change of the area at the moment. We got to freeze it though, at the moment when r is 200. It's a changing thing. It's a growing circle, but I'm asking for the rate of change of the area at this moment, at this instant. So this is a great problem. What formula? We need a formula that relates these variables. I think this one's very obvious. I think I want the formula called, what's the...
Area of pi squared.
The area of a circle. Thank you. I think I want the area of a circle. Let's write down that formula. the area equals pi r squared. He's right. That's the area of a circle. Hey, and if I had the radius, I could give you the area. There's no calculus here. This is just a formula. If you have the radius, I can tell you the area. If you have the area, I can tell you the radius. But that's not the question. The question was about the rate of change of these variables. So guess what I should do to this formula? I need this formula to start, but then you know what I want to do to this formula? I want to do this. I want to take the derivative implicitly with respect to t. There is no t in there. There is the variable a, there is the variable r, and I want to take the derivative with respect to t. And that's a new kind of strange thing for you. To me, it's an implicit derivative with respect to the variable t, which is not there. So when you run into the variable a, how do you do his derivative with respect to t? You write dA dt. That's how you do his derivative with respect to t. Go across the equal sign and do this derivative, please. Now, pi is a number. Sometimes students get a little confused that it's not a variable. Pi is a number. R is the variable. If I want to do this derivative, you do a power rule. You bring the 2 down, right, you guys? It's 2 pi. The 2 comes down. Pi r to the first. But now I need the derivative of r with respect to t. dr dt. That's the technique for doing an implicit derivative. Every variable you run into, you do its derivative, but then you tack on a dr dt, a dA dt, a dH dt, a dx dt, whatever variable it is. You guys okay? Okay. Yes?
So whenever you're doing a derivative in respect to another variable, every other variable in the equation, you basically just put a dr or dx or something over the thing?
I guess. See, right, when I was doing this derivative with respect to x, you know, I guess when it was an x, it was just a normal derivative. When it was a y, it was this abnormal derivative. It was this implicit derivative where we had to tack on the dy dx. When I do this derivative with respect to t, everybody's an abnormal derivative, or that's not really good. Implicit, everybody's an implicit derivative because I'm doing the derivative with respect to t. I don't know, I don't want to confuse you, but and this is not part of the problem, but what if you wanted to do this derivative with respect to r? Then you would write, oh, I'm doing the derivative of a with respect to r, and then when I go to the other side, I bring the 2 down, and I get 2 pi r, and do I have to write dr? No, I don't. When I'm doing the derivative with respect to r, I'm done. I mean, this is not what we're doing, but this might help contrast what we are doing. What if I was doing this? This is weird, but what if I was doing this derivative with respect to a? This is kind of weird, but I think I would run into, with respect to a, I think this derivative would be a 1. And then I would go over here and I would do 2 pi r, and then I would do the derivative of r with respect to a. I'm doing the derivative with respect to a. Again, this is not what we're doing, but trying to help you understand what we are doing. I'm taking the derivative with respect to the variable t, which is nowhere in the problem, and you have these 2 implicit derivatives in a way. Every variable is an implicit derivative. So, listen, the problem starts with you need an equation, and then you need the derivative with respect to t. And then hopefully from what you read, you can fill in and answer the question. I mean, the end of this problem is not difficult. What you read was that dr dt was a 60. Hold on a second, Carla. Dr dt, I can fill that 60 in there. DRDT is a 60. The 2 pi is a number. What about the radius? We said we were going to do this, or the question was, find dAdt at the moment when the radius was 200 feet. So I guess R is 200. R is 200. DRDT was a 60. That was all given. They're asking for dAdt. You know, it's easy. I got it. What is it? Whatever 60 times 200 times 2 times pi is, wow, 12,000, 24,000 pi?
Pretty much.
Pretty much. 24,000 pi. I wouldn't mind you decimalizing pi and giving me an actual number there. Can somebody do that? In other words, 3.14 times this is... 0.2. All right, thank you. What are the units on this? I could have kept track of my units a little better. What were the units on this 60? What was that? That was
Feet per minute.
That was feet per minute. What was about on this 200? What were the units on 200? Oh, that was 200 feet. There is no units on this number here. So this is feet squared per minute, which is what it's supposed to be. It's an area over time. It's feet squared, square feet per minute. That's what it's supposed to be. Wow. So at this moment, my area is expanding at 75,000 square feet per minute. By the way, a little bit later, when the radius is bigger, I think the rate of change of the area keeps changing. Hang on, Carlos. I think, let's do this again. Let's do this again a little later. We have not stopped this oil spill. It's continuing to grow. It's continuing to grow at this rate. The radius is changing at this rate, which I would call that a constant rate. It's not changing. Well, the radius is changing, but the rate at which the radius is changing is 60, constant 60. But I think the rate at which the area is changing keeps changing. That's complicated. The rate at which the area is changing keeps changing. At this moment, this was the rate of change of the area. I think a little bit later, when R is 300, let's just check it out. When R is 300, I think we'll have a bigger rate of change. This is still 2 pi. Now R is 300. This is later on after it grew a little more. And dRdt is still 60, but this area is going to be bigger. And I said that wrong. The area is not bigger. Well, the area is bigger, but this is not area. What is this? It's the rate of change of the area. Yeah, thank you. So the rate at which the area is growing is now a different number. I think it's a larger number. I think it's
113,000.
Thank you. 113,097 feet squared per minute. We won't worry about that 0.3. Thank you, though. Thank you. So that's one classic problem. There's what happens in 3.7 is there's all sorts of kind of problems that are looking at the rate of change of a couple of variables. The strategy, though, for all of them is come up with an equation and take the derivative with respect to t. And then read the problem carefully and fill stuff in and as needed. But you come up with an equation and you take the derivative with respect to t. That's a new thing. And so there's a bunch of good word problems in 3.7. Can I try another one?
You can't stop you.
You can't stop me. Let's try another one. Watch this one. Ready for this one? This is a classic. There's a ladder leaning up against the wall here. This is a ladder. This is a building. This is the floor. This is the ground. This is a building or something like that. And there's a ladder leaning up against the building. The ladder is not going to change length. The ladder is 30 feet long. The ladder's 30 feet long. But what happens is some sneaky guy, some jerk on the construction site, you know, he walks up here to the ladder, he grabs the bottom of the ladder and starts pulling it away while the poor guy's up there painting. So what happens if he pulls the base of the ladder away, what happens to the top of the ladder? It's gonna fall down the wall. Maybe that helps him paint along straight down the wall. Maybe it's just, but when he pulls the base of the ladder away, that's gonna fall. And what we say is he's gonna pull this base of the ladder away at 3 feet per minute. That's pretty slow. 3 feet in a minute. That's pretty good though. Maybe you should do it slow so the guy doesn't even know what's happening, you know. But the question is, how fast, which is kind of a rate, is the top of the ladder? How fast is the top of the ladder moving at the moment? And we gotta do it at a moment. At the moment, or the instant, or the moment when the base of the ladder is 20 feet from the building. Wow, that's a beautiful, this is a classic, beautiful question. Let's work on it. I think I should label something on that triangle there. What should you label the ladder? The ladder itself it's already labeled, I guess. It's 30 feet. It's not, so it's not changing, right? Is the length of the ladder is not changing. It's not a variable. Whoever's changing should be called a variable. What about this distance? Is it going to be changing? Yeah, because he's pulling it up, right. Let's call that X. What about this distance? We'll call it Y. Now it's your job to come up with an equation that relates these variables. Can you come up with an equation that relates these variables? And you're smart people. Pythagorean's theorem, I think, would help. I don't think I need any trig here because there's no angle. We're not talking about the angle. I mean, the angle will be changing, I guess. The angle will be changing, but there's no reference to the angle. We don't need to talk about an angle in this problem. So I think you're right. We're just talking about the three sides, and the relationship between those three sides would be Pythagorean's theorem, which I could write as x squared plus y squared equals the 30 squared. The 30 squared I can call 900 if you don't mind. That's awesome. That's what I needed. I needed an equation. And now what do I do to that equation? I take the derivative implicitly with respect to t. I take the derivative implicitly with respect to t. I should add that word in here. I'm taking the derivative implicitly with respect to t. It's easy to do too. I think I already did one like this today. How do I do this derivative with respect to t? It's how do I do it? 2x dx dt plus 2y dy dt equals this derivative, please? 0. Okay, you guys. In the way this problem was written and you know discussed to you here, what was given? This 3 feet per minute. Yeah, what is this 3 feet per minute?
dx dt.
Thank you. He's right. It's the rate of change of x, isn't it? Right? Okay, so thank you. That's a 3, and it's feet per minute. But sometimes I can just ignore the units and do this problem. It's a 3. dx dt is a 3. What are they asking for? How fast is the top of the ladder moving? What are they asking for? They're asking for dy dt. That's good. That's good. I'm going to call that my question mark. Let's see what else was given. At the moment when the base of the ladder is 20 feet from the building. What did they just tell me?
X.
They just told me X is 20. Right, you guys? All right, they just told me X is 20. Hey, that's pretty good. Now, let me think about this. If I start filling all this in. Yes, Carlos?
What's the difference between all these different variables, like the derivative of R, and A, and T, and all that?
I'm not sure I can answer that yet right now. Hang on a second. Let's work through this problem. These derivatives are rates of change, though, now. I'm not really thinking of them as, remember earlier in this chapter, derivatives are the slope of the tangent line. Now I'm thinking of derivatives as a rate of change between two variables. And it's no longer dy and dx. That rate of change was a slope. But now it's the rate of change between x and t. X, this variable x is changing at a rate of 3 feet per minute. So dx dt is 3. If I start filling this in, there's a 2. What's my x? 20. What's dx dt? 3. There's a 2. What's y? I don't know y. Hang on a minute. And what am I looking for? I'm looking for dy dt. That's what I'm looking for. So that's not good. I mean, now I treat this dy dt as my one unknown, and I wish I could solve for it. I can't solve for it if I don't know y. I need to know this y. What'd you just say? Oh, good job. And that happens sometimes. They told me x was 20. They didn't tell me y, but I can use the original equation. At the moment when x is 20, can you find y? Yeah, right? So I need that. So that's a little side work there. At the moment when x is 20, can we find y? Sure. 20 squared and y squared equals 900. Back to the original equation. That's a 400. When you subtract 400, y squared is 500. Can I just call y the square root of 500? Or 5 square roots of 10? Or no, 10 square roots of 5? 100 times 5? 10 square roots of 5, I think it is. Yeah, I'm going to write that if you don't mind. 10 square roots of 5. That's the square root of 500. All right? That's awesome. I mean, we're done, except for the little bit of algebra now. It wasn't too hard. This was a classic question. I'm going to solve this. This is 6. This is times 20. Is that 120? 120. I move it to the other side. It's negative 120. This is 20 square roots of 5 times this dy dt. I just multiplied those numbers. But I want to solve for dy dt, so I divide by this, and dy dt is negative 120 over 20 square roots of 5. Are you guys okay with that algebra? You can cancel the 20 into the 120. You can call that negative 6 over the square root of 5. Some people might want to rationalize their denominator. I don't ever really care about that, but that's negative 6 square roots of 5 over 5 if you rationalize your denominator. All these three numbers are the same. I might want a decimal version of this number. What is it? Anybody?
Negative 2.68
Negative 2.68. And what do you think the units are?
feet per minute.
It's dy dt. It's the rate of change of y. It's the rate of change of this distance as it's a changing distance. I guess it's falling. This ladder is falling down the wall at a rate of negative 2.68 feet per minute. Hey, why is it negative?
It's going down.
Oh, yeah, that's awesome. By the way, this x was positive because, yeah, it's increasing. I suppose some student might look at this picture and say, hey, you're pulling that thing to the left. You should call that negative. Don't do that. it's about, if the variable is growing, it's a positive rate of change. If the variable is shrinking, it's a negative rate of change. It really isn't always about left and right or up and down. Are you with me on that? When the variable is growing, that's a positive rate of change. When the variable is shrinking or decreasing, that's a negative rate of change. So this was a positive 3 because x was growing. We were growing x here. All right. Well, you should try some homework in 3-7. And on my take-home quiz, there's some of this. I don't want you to confuse this with other problems. I mean, we've talked about rate of change in other situations, but this is, they call this related rates. It's usually when there's no t anywhere in the problem, and you're taking the derivative with respect to t. All right, cool. I mean, there's a lot of problems we could explore in that topic, but I want to say we're done with that topic. And in preparation for our quiz a little bit later, do you guys have any questions? Anything on your mind you've been working on that you want to ask me about?
I have some questions.
What are they?
Oh, right. Hold on, give me 1 second. Just gotta pull it off.
Well, right. So anybody that has one ready? Yes, ma'am.
Yes, I think I'm ready.
Just a minute, please. What? Okay. Excuse me, please. I didn't quite hear her. What'd she say?
3.567.
Yeah, let's try that. 3.567. Let's see what that is. 3.567. Oh no. Oh no. Well, I didn't teach you this. You want me to teach it to you now? Y equals x squared, square root of 3x minus 2, all over x plus 1 squared. Wow. X squared, square root of 3x minus 2, all over x plus 1 squared. This is in 3.5, number 67. The directions say to use logarithmic differentiation. Logarithmic differentiation. And I have not really tackled this subject, I don't think. Have I? I don't think so. Well, now's a good time. So the question is to do this derivative. Look at it. Does anybody want to do this derivative? Who volunteers to? It's not too fun. It looks like a hell of a quotient rule, maybe, but the numerator is a product rule, so it's a product rule within a quotient rule. Might be some chain rule action going on in there too. Are you with me? She needs to listen. Everybody needs to listen. You don't need to do other things. Yeah, this is a tolerable product rule, quotient rule, chain rule. So to make it easier, they've got this idea called logarithmic differentiation. They say, before you do a derivative, take the log of both sides. The natural log. Okay, the natural log of both sides. All right. So now I got the natural log of this mess. I don't know how that makes it easier. Do you? How does that make it easier? Doesn't seem like that makes it any easier. Oh, well, I can use properties of logarithms. Logarithms have those special properties that you maybe remember. Logarithms have those properties that if you have the log of a product, you can bust it into a sum. If you have the log of a division, you can bust it into subtraction. You know what I mean, right? If you have a log of something with a power on it, you can bring the power down front. Now, they wanted me to do a derivative. But I guess I'm avoiding the derivative, and I'm going to use log properties to sort of change the look of this thing. Make it look easier. Maybe it'll be easier. Let's see what happens. On this side, I still have just the log of y, but on this side, I'm going to change this. Now, if you don't mind, I want to do a few steps at once. Up in the numerator, it's a multiplication. That's going to turn into the log of x squared plus the log of 3x minus 2 to the half. Is that okay? You have multiplication, you bust it into the addition of two logs. The denominator has you're dividing by this. Well, that means I will subtract the log of x plus 1 squared. That's using log properties to bust that up. I can do one more log property. The one about the exponent. I can bring those exponents down front. Bringing these exponents down front is not doing a derivative. It's using log properties that say I'm allowed to do that. So one more here. I'm still writing. I'm still just cleaning and playing with log properties. Wow. There I am. Using log properties to clean that mess up. But now, the derivative might be easier. I think now I'll do a derivative. And, you know, originally, this would you call this original problem an implicit derivative? Would you? No, it's not implicit. There's one y all by itself, explicitly in terms of x. It was an explicit derivative. But now that we took the log of both sides and used all these log properties, now it's sort of an implicit derivative. I walk over here and I should take the derivative with respect to x. When I take this derivative with respect to x, what do I get? 1 over y, I mean that's the derivative, 1 over y times dy dx. That was a little implicit part of this derivative. Yes, Carlos?
Over there where you have the dash 1, I get 3x minus 2 to the 1/2. I see when you took the derivative then it became 1/2 natural 1, 3x minus 2, but how come the 1/2 didn't turn to negative 1/2?
Yeah, okay, listen carefully. I have not done any derivatives. You misspoke right there. When I turned this into addition, I was using log properties. When I brought this 2 down front, I was using log properties. I was not doing a derivative. So moving these exponents down front is not, I'm not doing a derivative. Those were log properties. So all these steps were log properties, not derivatives. Hey, here comes the derivative step right now. This is the derivative step right now. Now I'm doing a derivative. And it's going to be an easy derivative. Watch how easy it is. Because we've avoided all those product rules and quotient rules, haven't we? By using logs and busting this up, we don't have any product rules or quotient rules. It's the easiest derivative there is. How do you do the derivative of log x? The 2 is multiplied, and what's the derivative of log x? 1 over x. The 1/2 is multiplied, and I want to do this derivative of this log. 1 over 3x minus 2. Anybody want to say anything else?
Chain rule.
Chain rule. Thank you. Multiply by 3. Thank you. Next, there's a 2, and I want to do that derivative, please. See how easy the derivative was? We avoided product rules, quotient rules by logarithmic differentiation. The derivative is over, except, wait a minute, where's the derivative? Where's the derivative? Oh, here's the derivative, right? I mean, the derivative is dy dx, right? The original function was y, and his derivative is dy dx. So how do I actually get dy dx by itself? Multiply by that y? Multiply that y to the other side. Okay, great. I really like that. Multiplying that y to the other side. Here we go. dy dx is that y times that long string of stuff. I'll clean it up just a little here. That's a 2 over x. That's a, that's a 3 over 2, 3x minus 2. Is that okay with you? And that's a negative 2 over x plus 1. You guys okay? Technically, before you finish this problem, you ought to go ahead and put y back in there. What's y? Oh, there's y.
Oh.
Well, hold on now. I mean, I'm just going to write it. That y is that. Hold on, Carlos. Hold on. That's the y, right, you guys? And then it's multiplied by all this. Now, guess what your book would do? You guess. Now, you tell me. What would your book do? Or some really bored mathematician, what would they do now? Get a common denominator. We're done with the derivative, by the way. But you could get a common denominator. You could distribute, perhaps. Get it clean all. You could keep cleaning. It's kind of funny. I'm trying to sell you logarithmic differentiation like it's a shortcut. It really helped me avoid. What did it help me do? It helped me avoid product rules and quotient rules, right? It was cool. Except it makes me do all this common denominator work at the end. So I don't know if I like it or not. You know what I do like it for? I like it for this. You know, I don't think I ever taught you a rule for this. I think I taught you a rule for e to the x. Does anybody know how to do the derivative of e to the x?
E to the x.
It's the derivative of e to the x is e to the x, yeah. I don't know if I did a good job of explaining this rule to you or telling you this rule. If it's a 5 to the x, it's not an e to the x. It's a little different. There is a rule for it. I could just make you memorize it. Or we could do logarithmic differentiation. Watch this. Before you do a derivative, take the log of both sides. You get the log of y and you get the log of 5 to the x. What does that do for me? It makes me, I can move this x down front using log properties, not doing a derivative. I haven't done a derivative yet. But using log properties, I can move that x down front. And now I think I want to do a derivative. Right now I want to do a derivative. Here we go. Oh, by the way, now it's sort of an implicit derivative. Do you agree? I mean, it's because I got this log on this y. How do I do this derivative? I've got to do 1 over y dy dx. Hey, this derivative it's very easy, but I suppose you could confuse yourself. It's just, I want you to realize it's just x times a number. That ln 5 is a number. So how do you do the derivative of x times a number? Like a 6x. What's the derivative of 6x? 6. So what's the derivative of x times this number? That number. Right, so it's this number. If I want the derivative, I have to multiply by y. So the derivative is, this y shows up here. And what is y? There it is, 5 to the x. 5 to the x times the ln of 5. That's the derivative. You can memorize that rule. That's actually the rule. I don't think I ever taught you that rule. The rule is, how do you take the derivative of a to the x when your base is a and not e? And the rule is, it's just himself times the natural log of a. But I just proved that rule to you by using logarithmic differentiation. Taking the log of both sides and then doing the derivative. By the way, that rule kind of works on this. The rule might be, it's e to the x times the ln of e. But we never write that because, you know what the ln of e is? 1. So that rule applies to other bases when it's base 2 or base 5 or base 7. That's the rule. When it's base e, it's also the rule, except the ln of e is 1. So nobody ever realized that was the rule. All right, listen. This was in the homework, and it was worth going through one time. I don't think I want to do 12 of these. I like this little mini version of it because it proves this little rule. I don't really like these kind of problems that well. It was fun, and it got the point. Maybe the point got across, but I don't think these showed up on your take-home quiz anywhere, and I don't think they are going to show up on your tests next week. I don't think so. But it's still worth doing. It's fun to do. Yes, Carlos?
Over there on the right side, from the top to the bottom, what did you do?
Well, I replaced that y with what y was originally. What was y? Oh, there it is. Y equals that, and this y got replaced by that.
But why?
Because I can. Y equals this, and so I can replace this y with this. To get the derivative in terms of x's, I could leave the derivative like this. It has y's and x's. It's an implicit derivative. We've learned that it's okay to have implicit derivatives. It's okay that the derivative has y's and x's in it. That's what happens in an implicit situation. So I can leave it like this, but we can clean it up by replacing y with what it is. Y is this. Other problems? Let's move past this problem. Yes, ma'am.
Number 7.
In where?
3.5.
In 3.5, she asked about 7. Let's see what that is. In 3.5, she asked about 7. Ooh, yeah. X cubed, y cubed minus y equals x. Okay, that's a classic. Number 7 in 3.5. X cubed, y cubed minus y equals x. Okay. And the question is, do the derivative. And do I need to say the word? What's the word? Implicit is the word. I mean, you just assume that, right? You just know that. You're getting good at that, I guess. All your x's and y's are mixed up. You got an implicit situation. What's funny about these implicit derivatives is when they have these x's times y's, you have to treat that as a product rule. So here I go. I want to take this derivative implicitly, and I have to treat this like a product rule. You ready? The derivative of the first, 3x squared. Write down the second, plus. Write down the first, and here comes the little implicit part, I guess. I have to do the derivative of y cubed. 3y squared dy dx. Yep, good job. Minus the derivative of that y. dy dx, or 1 dy dx, or right. Equals, on the other side, equals the derivative of that x. 1. And we're done. We're finished doing the derivative, except now there is some algebra involved because we technically, where's the derivative? The derivative is that dy dx term, and we would like to solve for that. And so now it's an algebra game to solve for that. How would you solve for it? Okay, I think I heard you say, first move this guy to the other side. That'll leave you x cubed, or I'm going to write 3x cubed y squared, this is this guy, dy dx, minus dy dx, and you're saying you move this to the other side, it's 1 minus 3x squared y cubed. Okay, now what? How do you solve for dy dx? Factor it out. That's usually the key. Get everybody on one side that has a dy dx and factor it out. If you factor it out, you're left with 3x cubed y squared minus 1. This side is this, and now how do you solve for dy dx? Divide by that quantity. Yeah, that's a good problem. That's a good problem. Here it is. Yeah, that was good. Other requests?
3.4, comparing 51 with 59, and like this basically squaring stuff, and functions are squared.
Yeah, so you want me to compare 51, specifically 51, to 59, or is that what you just said?
Yeah.
Yeah, so, and I could specifically look at those or kind of make up my own, but, well, okay. So 51 is y equals the sine of pi x squared. Y equals the sine of pi x squared. And then in 59, y equals the tangent squared of 5 theta. The tangent squared of 5 theta. They're using theta as a variable. Do you mind if I change it to x? I'm going to change it to x. 5x. But, you know, what's she asking me here? I think I know what she's asking me. She's looking at those squareds, and how do I deal with these squareds differently? They definitely are different. Who's being squared right here? Not the sine function. The sine function is not being squared. The angle is being squared. The pi x is being squared. Who's being squared over here? The tangent function. The tangent of 5x is being squared. That's the way we write exponents on trig functions. We write them like that. If the exponent's out here, it's just on that angle. It's not on the entire trig function. Is that confusing to you? I mean, maybe she asked me because it was sort of confusing. You know, an extra set of parentheses here. Now, who's squared? The entire sine function is now squared, but that's not what it was. All right, so maybe I can do this derivative. I have to kind of realize. Let's see. It's a chain rule, and I'm working my way outside in. Who's the outside function here? Sine. It is sine. And so what's the derivative of sine? Cosine. And the angle that's in there is the angle that's in here. The derivative of the sine of that is the cosine of that. But now I should do the derivative of that, that angle. I should do the derivative of that angle. That's the chain rule. How do I do the derivative of a little pi x squared? Maybe I bring the 2 down, and then it's a pi x to the first. But then technically I should go in there and take the derivative of the little pi x. It's a number times x. What's the derivative? Pi. That's the answer, you guys. I can clean it up a little bit. I would like to move all this stuff kind of out front. And what is it? It's a 2 pi squared x. Is that okay with you? In front of cosine pi x squared. That was kind of funny. You know, I want to show you something. I could have avoided a little bit of that work. If I just would have squared that, watch, I could write this differently. I can write this as the sine of pi squared x squared. I don't know. What happens now? What if you do the derivative now? You ready? I'm doing the derivative now. The derivative of the sine? Cosine. Pi squared x squared. The derivative of this angle now. The pi squared is a constant. The x squared is your variable. You bring the 2 down and you're done. 2 pi squared x. Is that okay? Bring the 2 down from the x. Bring the 2 from the x. The pi squared's a number. Leave pi squared a number. Bring the 2 down from the x and you're done. Which is this Sometimes it's cool to do a little algebra before you do a derivative. Is that what I just did? I did a little algebra work before I did the derivative. Hey, I've practiced this a lot, I think. I love these trig functions that have a power. This is the tangent function being squared. So how do you deal with the tangent function being squared? You take the derivative, you work your way outside in, and what's the outermost thing?
Squared.
Something squared. Thank you. Something is squared. So you bring the 2 down, and now that tangent function is to the first. Thank you. It's to the first. Now you're done with the power. You have to do the derivative of what was inside that power. What was inside that power? Oh, a tangent function was inside that power. So now what's the derivative of a tangent function? Secant squared of 5x. The derivative of tangent of x is secant squared of x. Or the derivative of tangent 5x is secant squared 5x. But I think I better go inside that little tangent function. There was a little thing called 5x, and at the end I should do the derivative of the 5x. 5. I did a power rule on the tangent function. I did the derivative of the tangent function, and then I did the derivative of what was inside the tangent function, the 5. That was a little 3-layered chain rule. Not much to do to clean that up, except maybe move the 5 out front and call it a 10. Is that okay with you? But that's kind of it. Yes, sir.
Could you do number 9 of the take-home quiz?
I think so. Number 9 on the take-home quiz. Yeah, let's do that one. And then we need to kind of quit, I think. But let's do this one, and then we'll quit. Or take a break. And then. So he's asking about the take-home quiz. There's a problem number 9, and it looks like this. The cube root of 12x minus 42 squared. Wow. The cube root of 12x minus 42, that quantity squared. And then it asked me these interesting questions. Where does it have a horizontal tangent line? Where is it non-differentiable? Why is it non-differentiable? This is good. These are good questions. But in order to answer any of those questions, what should I do? I should do a derivative. But you're in calculus and you're in chapter 3. When in doubt, do a derivative, I guess. So I need to do a derivative. You know, in order to do a derivative, I think I would rewrite that as 12x minus 42 to the 2/3. Okay, so let's do a derivative. The derivative is 2/3 12x minus 42 to the negative 1/3 times the derivative inside. The chain rule says you better do the derivative inside, which is 12. This is beautiful. Watch this derivative. When you clean up this derivative, I think I'll move this to the denominator. This thing is to the negative 1/3. I'll move it to the denominator and it'll be 12x minus 42 to the positive 1/3. By the way, that's a cube root, but I can just write it as a 1/3. And what's left in my numerator? 2/3 times 12, which happens to be 8. This is beautiful, you guys. Let's try to answer these questions. Part A was, where does it have a horizontal tangent line? By the way, when they say where, that's usually the x value. We're looking for the x value, where that happens. Maybe the x and y value, maybe a point. But you know this game. We've been practicing this. A horizontal tangent line is when the slope is 0. The derivative is 0. Look at this derivative and tell me when it's 0. Never. It's 0 when the numerator is 0, and the numerator is an 8, so it's never 0. You guys with me? That was very easy, actually. It turns out never is the answer. Never gonna be one. Ain't gonna happen. Whatever, just say never. What's the next question? Where is it non-differentiable? That's different. When it's non-differentiable when the derivative is undefined, not 0. See, up here we just asked when is the derivative 0? That's what that was. Now we're asking when is the derivative undefined? That's what non-differentiable function means. So when is this derivative undefined? When the denominator is 0, I guess. And that's pretty darn easy. When does that happen? I mean, you can do a little algebra. When that denominator equals 0. By the way, I just ignored the cube root. I mean, it's going to equal 0 when that quantity is 0. And it's pretty darn easy. Move the 42 over, divide by 12. X is 42 twelfths, or
3.5.
3.5. Or 7 halves, I got you. 7 halves, or 3.5, he says. Okay, cool. That's it. That's a non-differentiable point. It's not undefined in the original function. It's not undefined in the original function, but it is undefined in the derivative. And that makes it a non-differentiable point. And my next question is why? And what I mean by that is it an endpoint? We discussed how it could be an endpoint, a sharp point, a discontinuity, or a vertical tangent line. What I should do, perhaps, is pick up my graphic calculator and graph this original function and see what it looks like. I think it looks like this. And therefore, I would say sharp point. I should have let y'all finish that one, but that was cool, man. That really wasn't that hard of a problem, and it hit some good concepts in kind of an easy way. In a way, you had to. That was good. Listen, we really should quit. We're running out of time here, so I'm gonna quit. I'm gonna hit off on this thing if it's still going.